With all of that preamble done, I am now extremely happy to welcome Nellie Wilson. She's the Global Head of AI Services for Weather and Climate at Google. Welcome, Nellie.
Thank you so much, Jay, for having me, and thank you all for joining today. We really appreciate you taking time out of your busy day to come and hear more about weather and what Google is doing in this very, very exciting space. I currently, as Jay said, lead our AI services team for weather and climate here at Google Cloud, and I always like to say, like, kind of, why did I get interested in weather? How did I get started? I grew up in Florida, and then I spent many years living in Texas. And living in both of those places, I lived through hurricanes, and I also lived through crazy winter storms, really getting to experience how the atmosphere is affecting everybody's day-to-day life. And after having seen many people, friends, family, coworkers go through similar experiences, weather is really top of mind for folks nowadays. And as we see natural disasters are becoming more prevalent, there's much more changing weather patterns. And so really being able to have as much insight and focus going forward for how we can help companies, organizations, governments, and people change and prepare for the coming years and for their day-to-day lives with weather is a really exciting moment to be able to help as we go forward in how we're moving. I don't know if it's just me. I think we might have lost the screen there. But I'm happy.
Just bring those slides back up.
No worries. But I'm really excited to be able to share with you all today about what we're doing at Google and how we're continuing to really tackle this problem of weather and weather predictions. And so when we look at today, what we're going to be covering, perfect. We're going to walk through why is this important? Obviously, weather affects lots of people, but really, why is this an area that Google has invested a lot of time and resources in to be able to drive the industry forward? Then we're going to touch on what is it being used for? So how are we actually utilizing this in our day-to-day organizations and processes and workflows to be able to see how we can make the world a safer and more resilient place? And then what we're actually launching and bringing to market, how you all can get access, and we'll wrap up with some Q&A so that you're able to ask any questions and hopefully continue this discussion. It is such an exciting space, and being able to have more people involved in bringing their perspectives and what use cases you all are trying to tackle is a great way that we can continue to collaborate and learn from one another. So I love to start off by really thinking about Google and why we got into this. We are an AI first company, and we love tackling hard problems. And as we all know from kind of the running meteorologist joke of, if they say to take an umbrella, you don't need one. And when they don't say you need one. And so we know that weather is a pretty hard problem. And so when we started to think about hard problems, we love solving hard problems at Google, and we love starting hard problems with AI. And weather was one that really resonated with us, because as we see, weather affects every person, every company, and every industry around the world. And knowing the level of impact that that has on our societies, on our organizations, we're really seeing how this has an impact from food production and crop yield predictions in agriculture to being able to do better energy forecasts and make our grid more resilient, and also be able to prepare for natural disasters, to even just the simplest thing of planning your day. And so we love being able to have something that's shaping every aspect of our lives. And it's actually, weather is a very unifying concept. It's something that everybody experiences around the world, and being able to help provide our technology to the world through weather and be able to bring the resources that we have to be able to hopefully predict it more accurately and efficiently is something that gets us really excited. So I want to go ahead and start out by talking a little bit about how are we thinking about weather. And for some of you, you may already be with kind of the weather ecosystem and how weather models have traditionally been developed. But there's been a lot of new developments in the last couple of years. And the most profound one being the difference of numerical weather predictions, or NWP models, versus AI models. And this is really starting to kind of differentiate between the more traditional aspects of numerical weather predictions. And so for anybody that's not familiar, numerical weather predictions are really centered around being able to take all of the different physical atmospheric components and really trying to take almost code manually the physics equations of the atmosphere into a model, and be able to do that where we're taking all of these different components, creating these mathematical equations, creating an algorithm that then can process them. And it's very energy intensive, very compute intensive, because you're trying to pretty much code the world, which is no easy task, but that has been the way in which we've traditionally done a lot of our weather predictions. There's now this newer focus that is bringing in the concept of AI-driven weather models. And we took a bit different approach here from the Google stance compared to the traditional path of really focusing on training on many decades of historical data. So we actually wanted to say, instead of trying to manually code all these physics and atmospheric elements into a model, what if we just give it a huge amount of data, let it learn from that data, and then it will go ahead and be able to process and provide answers that perhaps humans weren't even able to comprehend or pick up on or code into the algorithm to be able to then process or figure out what that would look like. And so when we did this, we were really, really excited about the results, which I'll touch on in a couple of moments. But this is really kind of the key kind of baseline or differentiator between the two versions of the models that we're seeing in the overall weather space and ecosystem. And then the other differentiator that we see a lot of kind of components centered around are either deterministic or probabilistic models. And deterministic is where you're setting a certain amount of inputs and you're getting one outcome or one weather forecast from your weather model. Probabilistic forecasts are where you are actually getting multiple versions, many times called ensembles. You're getting multiple different outcomes of these forecasts. And the great part about this is that it really helps provide different viewpoints of being able to give you kind of a range of possible outcomes and then their associated probabilities, where the deterministic is really focused on providing that single best guess forecast. Not that one is better or worse than the other. It's really comes down to what is the use case that you have and what is the outcome that you're looking for that is best able to suit that. And we see that there's different models that have been populated across the weather ecosystem over the last couple of years for these different purposes. So GFS and single run WRF, those are your deterministic NWP models. Many of you may have used these in the past, but they're kind of the industry standard and widely adopted in this space. Our version for our deterministic AI model is WeatherNext Graph. And so we've gone ahead and created this. It was published in Nature, the scientific journal, a couple of years back. And we went ahead and open sourced the model so that everybody is able to go ahead and view it, experiment with it, and be able to use it for academic and scientific purposes. We then also went ahead and released WeatherNext Gen. And this is our probabilistic AI model, which comparatively for the NWP probabilistic models are the ECMWF, EPS, and also the GEFS. So if anybody has used those are the equivalent. And what we're really excited about WeatherNext Gen, we also published in Nature last November, December timeframe. And what we're really excited about is the response in being able to see what those risk probabilities are. There's been a lot of interest in being able to predict what are the tail end curves and what are some of those outcomes that, again, low likelihood, but could be a potential outcome, and really being able to see the full breadth of what could be happening. And being able to understand what are those different weather scenarios, being able to assess that forecast uncertainty, and then plan accordingly. So this is kind of just to set the foundation for where we are and how we view kind of the weather landscape and what we are continuing to build as we move forward. Now, to kind of go back to our weather models, And what we are really excited about is that it's not just one model that we are trying to build. We are really trying to focus on the full totality and time horizon of how these models are being created. And so we've gone ahead and created 3 different models that are centered around different time horizons. And the first being MetNet. So this is our nowcasting model, which is focused on the 24 hours or less space. And it's actually what powers Google search today. So if you type in weather in New York City, this is the weather result. This is the model that's creating that result for you in Google search. We then have our medium range forecasting. So when we think about that 2 to 2 weeks out range, that's really where WeatherNext Graph, which goes out 10 days, and I'll touch on more in a second, and WeatherNext Gen goes out 15 days. This is really where we're centering a lot of our efforts around medium range forecasting. We're really excited because we have now released these models, not only as open source models for academic and scientific purposes, but we also have released experimental data sets available in Google Cloud for commercial purposes, and being able to incorporate some of the additional advancements of our newer versions of these models and providing that innovation to our cloud customers and to folks that want to be able to incorporate them into their organizations. So I'll be touching more on WeatherNext Graph and Gen in a second, but our last time horizon is really when we start to look out further into that 6 months to a year, 5, 10, even 20, 30 years, and really trying to do more climatology. We're really focused on being able to do longer term predictions to be able to help from agriculture with kind of subseasonal and seasonal planning, crop yield prediction, best time to harvest, and also being able to understand how is the climate changing over the course of the next year, 5, 10 years, so that we can do better planning for our cities, for our grids, for really being able to make sure that people are well equipped for how things are changing wherever they are located. So that's our neural GCM model. So this is our kind of weather suite at the moment of models that we have created, and that we're really looking forward to having customers and folks implement across their organizations, and being able to also have the scientific and academic communities participate in these processes of testing and being able to see what are additional factors that you all discover, and how we can continue to make these models the most efficient and accurate possible. So I'm going to deep dive into our WeatherNext Graph and our WeatherNext Gen models in particular, because the medium range forecasting that we've seen really great success with, and also is for our area of focus, an area that we're investing a lot of resources, as there's many use cases that are highly affected by this time range. So for WeatherNext Graph in particular, just to deep dive a little bit more into this model, this is our deterministic 10-day ahead model, and we are really focused on being able to provide 80 variables at a global 0.25 resolution. So the great part with our models is that they have global coverage. So not just in one location, let's say North America or EMEA, but they are actually global models where we're able to provide forecasts for every area of the globe, which is really great when we look at being able to provide more equity and access to every person around the world, which is a core mission of what we're doing with Google and the products that we release. We're providing variables, the typical ones such as wind, temperature, precipitation, humidity, being able to do things like that. But also, as we start to evaluate further areas into the atmosphere, we also categorize at all the different pressure levels going up into the atmosphere. So we start in the troposphere, and then we go up into the stratosphere, being able to categorize all these different elements. And the graphic on the top right, you kind of see this grid dynamic of we have a global grid where we're predicting forecasts around the world. And again, going up into different layers of the atmosphere where we're able to predict all those variables at each of those grid points. We're really excited that this is outperforming the industry-leading NWP models. When compared to our HRES counterparts, we're beating the HRES outcomes over 95% of the time for their metrics. So when we look at, again, in terms of accuracy and forecasting, really being able to do this not only from a more accurate standpoint, but another really key differentiator is the level of efficiency that AI forecasts bring. Typically, those NWP models, as I said earlier, are really compute intensive. And one of the big differentiators with AI models is that they're much less energy and compute intensive once they've been trained. And so being able to run inference in a matter of minutes versus more traditionally with NWP models, whether that's hours, if not even days, depending on the breadth of those forecast simulations that you're running, it's really, really exciting to be able to see that with all the discussion around AI and how it's impacting the grid and how energy is so in demand, making sure that we're creating new technology that actually is making it even more efficient and more accurate to run our forecasts and be able to have the best outcomes that we can. So really excited to see the results of the work that have come together in that way. And then for the actual level of granularity, we do produce these forecasts every 6 hours for WeatherNext Graph. These are released publicly through BigQuery and Google Earth Engine, and we have both historical and real-time data available. So we will go ahead at the very end, I'll touch on how you can actually get access to this, but being able to provide these forecasts every 6 hours globally. And then the last area that I want to touch on this slide is in the bottom right, you'll see kind of a scorecard looking mechanism. And one of the areas that Google has actually put a lot of investment into is how we're evaluating our weather forecasts, and specifically with the AI models. It's really important to think about how you're comparing kind of apples to apples, different weather forecasts and evaluations. And so we created a tool called WeatherBench, which we've open sourced and made freely available to the public to be able to utilize and compare different forecasts from one to the other. And you'll see here, these forecasts are comparing WeatherNext graph to the HRES forecast. And specifically, the blue sections are where GraphCast is outperforming, and the red sections is where the HRES forecast outperforms. And I know it's a little small, but pretty much that red line across is at the very, very, very top of the stratosphere. So it's when you get into the very top layer, HRES outperforms. But for everything else right now, and again, we're continuing to improve and iterate on these models, GraphCast is outperforming on these metrics. So really excited about what we're able to do with GraphCast and being able to do that with a fraction of the computational cost, and again, being able to have that global coverage at that 6 hourly level resolution. And then our next model, which we released in the end of last year, is WeatherNext Gen. So this is our 15-day ahead model where we're focused on probabilistic forecasts. And very similar to WeatherNext Graph, we also predict at the 0.25 level resolution. But this one, we go out 15 days. So we're able to go out a bit further, and we provide these forecasts at a 12-hour level resolution temporally. So being able to have further out and the 12 hours, but again, also global. So we're glad that we can continue to have that level of coverage. And really with these probabilistic forecasts, it's really focused on being able to complement the deterministic forecast of weather. Obviously, it's hard to always know exactly what is going to happen for that forecast. And so wanting to be able to see the full range of possible outcomes and understanding what are those different probabilities for different events of interest. And perhaps a hurricane is coming. And so it's even more important to be able to have more visions of where kind of from a spaghetti model look is the best way I like to compare it to, of really being able to understand what that looks like and have as many different simulations or ensembles of what this possible forecast can be. And so we go ahead and specifically with WeatherNext Gen, when compared to ECMWF for the ENS, which is their ensemble forecasting model, again, we're also beating them over 96% of the time for when compared against 1,300 different targets and variables. And you'll see here for the scorecard on the right, the blue again is where WeatherNext Gen is outperforming, and then the red is where ENSs. And really this focus area that we're continuing to address is really in kind of the immediate first 6 to 12 hours of being able to have more accuracy. There's a lot of change in that time frame typically, and so we're continuing to fine tune and work on our models to be able to have more of that accuracy in the short term. But again, that 2 to 15 day range, we're really doing well in being able to predict those outcomes. So I know that it's one thing to be able to talk about all the research and the work that we're doing and the excitement about the actual technology, which is fantastic. But we're big believers here at Google of it's one thing if it's just research, but it makes it so much more impactful if we get it out into the world. And that's been a huge focus for us of actually testing these in real life with real applications. And one that we were really excited about, the New York Times wrote up a profile last year on Hurricane Beryl. And for any of you that are from Texas or familiar with how this hurricane went, originally the European and American forecasts starting out were actually predicting that Hurricane Beryl would hit in Mexico. And a couple of days before they corrected their assumptions, WeatherNext graph predicted correctly that it would actually make landfall in Texas. And it really was very closely aligned with the actual path of where this hurricane ended up landing. And when we think of the amount of impact that this can have from not only helping local citizens prepare for a hurricane, but also being able to equip energy companies and where their repair crews need to be stationed and still stay out of harm's way during that hurricane, but be as close as possible to get the grid up and running as soon as that hurricane blows through, helping local government prepare and equip citizens for what they need. And then obviously being able to help all the logistics companies and make sure that they can get supplies in after this hurricane goes through. Just so much impact of being able of what a couple extra days can do in not only preparation, but also in what that results afterwards and being able to help people resume their lives as quickly as possible. So we were really excited to see, again, the impact that this has and being able to incorporate it into not only from a hurricane perspective, but also from a business and operational flow. And so how do we actually utilize these weather forecasts? I will say there are many different ways. And one of the exciting things is that weather does affect everyone in every industry. And so we've been having a lot of conversations across every single industry, but a couple of the use cases that we've seen a lot of excitement around. The energy sector has been hugely interested from a grid supply and demand prediction focus. We all know that certain summers are getting very, very hot in regions of the country, and being able to make sure that grid can actually, one, predict what that looks like, and then also being able to make sure that we're able to respond with the necessary supply and perhaps start to balance and offload different areas to make sure that grids don't have blackouts and that we can be as proactive as possible in making sure that people have the energy they need during the times that they need it. We've seen things around crew scheduling for being able to make sure that repairs are done at the right time in relation to weather effects. Site selection for specifically renewables has been very much of interest. And really when we look at also the agriculture and the public sector community, really being able to do better predictions around crop yield, being able to do heat wave and drought planning has been a really big one, not only being able to do precipitation forecasts, but also making sure that we're able to understand what those temperatures will be. So then that way crops do not go along with livestock or experience any kind of prolonged damage, but being able to get ahead of what those weather effects will be. Manufacturing, logistics, and the finance industries have also been another area of a lot of interest for specifically being able to do capital markets trading, but making sure that we can get people damage assessments and claims management faster after a natural disaster happens. If we know where it's going to hit, being able to have crews go out in advance or be ready to go out after something goes through so that people can get the help and assistance they need ahead as quickly as possible after an adverse weather effect occurs. And then being able to do more optimized route planning. We've seen this a lot with flights and with trucking companies, being able to predict, obviously, weather, especially around the holidays, it always seems like, has some pretty adverse effects. If there's a massive snowstorm or there's a big rainstorm or wind or lightning, being able to have more efficient planning and delay management in advance so that people can plan accordingly with our forecast is really exciting. And then lastly, the retail and entertainment space has also been interested in being able to do better demand planning for merchandise and being able to ensure that if it's raining, can we put umbrellas at the front of the store so that people can get what they need, again, according to what the weather is outside. And then also how we can incorporate this into broadcast and really being able to provide more assistance to meteorologists. There's been a lot of interest around AI weather models. And so being able to understand what are those different use cases where we're actually equipping the experts with more informed decision-making power. So then that way they can go ahead and take those insights and share them with the broader communities that they reach. And so we're really trying to make sure that we're covering the full gamut of everything that is possible. And again, really being able to make sure that this is accessible to as many people as we can make it. So I'm going to show just a quick demo of what this can look like specifically in the energy space. We were at CERAWeek, which is one of the largest energy conferences in the world earlier this year, and a lot of interest from the energy sector, and especially around crew safety and making sure that we can keep people safe with weather. Obviously, weather has electricity, and electricity in certain situations, as in rain, it can be very, very dangerous. And so we actually went ahead and created a demo of what this can be and how we can envision a future where we're able to have better crew management and prediction, and yet also still meet what customers are needing and make sure we're still satisfying kind of the responsibilities of what an energy company has to do on a day-to-day basis. So I'll walk through this demo real quick, and I know it's a little small, but hopefully you all can see. Pretty much it's saying I'm looking to schedule a lineman repair crew for a transformer repair. Can you tell me what day is best based off of the temperature? So it goes ahead and provides that. It says like there's a good chance of rain that's coming though. So how does this affect my crew? And then Gemini is able to go ahead and actually walk through what are the electrical hazards, the safety hazards, to be able to showcase what that can look like. And then it actually recommends an additional type of work, such as line repair crew, to be able to say, instead of the work out front, let's go ahead and actually have them do something else that doesn't put them at risk of electrocution. So it says, is that original crew qualified to go ahead and do the line markings for these gas lines, which was the recommendation of that other alternative? It says yes, and that it has that. And then it says, what is the best day to actually do this work? Based off of this kind of change in weather. And so it recommends a new day. And then it goes ahead and says kind of the recommendation of it's actually going to be a bit hotter than normal. So how should I go ahead and equip my crews, or anything I need to change because it's actually going to be much warmer for this other task? And so it goes ahead and says it normally takes 90 minutes, but you should give an additional 30 minutes based off of the crew and to make sure that they can do this safely. So really, when we look at kind of the full totality of this, it's really being able to take weather, and obviously weather forecasts have an innate value, but it's really embedding it into the business and the operational workflows that drives the most amount of impact for an organization. And that is what we're really excited about, is really kind of that abstracted layer up of being able to have a much greater level of impact in being able to take this knowledge and insight about weather and then embed it into your organizational workflows. So that's just one example of what we envision, but in real life, we have customers that are doing this already. So we're actually partnering with Carrier. They're a global leader in intelligent climate and energy solutions, and they're one of the first customers that have been adopting WeatherNext. And we're really looking forward to be able to bring this to the world because we're collaborating with them on implementing their home energy management system, which they call HEMS, which combines dedicated battery storage with advanced HVAC systems to optimize their energy usage by leveraging AI-driven insights from WeatherNext. So Carrier's HEMS system will dynamically adjust the HVAC energy consumption based off of real-time weather forecasts and grid conditions, which will help enhance our energy efficiency and grid resilience while maintaining uninterrupted comfort to the homeowner. So we're really excited about being able to have this come into not just in the academic and scientific communities, which is super, super important, but being able to make sure we're bringing this out into the world and getting it out to as many people as possible to have as much of a positive impact. So lots more great things with Carrier ahead and many other customers. But again, want to be able to share, we are doing this, we are implementing it, and looking forward to many more customers that we can announce those collaborations with publicly. So what are we launching and how do you all get access to this today? We have our launch. Our forecasts are actually available today via BigQuery and Earth Engine. So you can access it directly through Google Cloud. And these are our 10 and 15 days. So WeatherNext Graph and WeatherNext Gen at that 6 and 12 hourly time steps that are currently available. And we have both the historical and the real-time forecasts. So those are all located there, and it's completely free to access them, whatever consumption you generate on top, so whatever queries, but it's pretty minimal, again, because we have optimized these forecasts so much for being able to have the least amount of compute and the least amount of kind of energy associated with actually being able to get the answers that you're looking for. So that's the first way in which you can access them. The second way is if you want to build a customized weather model. So this can be increased granularity for the actual data sets. So we do have hourly data sets that we are working with customers. And so being able to have more granularity around the data, being able to have more increased spatial resolution, or being able to fine tune these models. One area that we've got a lot of interest in is for WeatherNext Gen in particular. Currently, the default is 50 ensembles that are generated with each forecast. However, certain use cases require having or want to have, let's say, 1,000 ensemble members, really being able to see what those tail end situations are for the forecast. And so if that's of interest, feel free to reach out at WeatherNext-Google WeatherNext-cloud@google.com, and we'll be able to go ahead and help figure out what is that kind of custom AI weather model you may be looking for, and we can really explore what's the best fit to make sure that we're meeting what you're looking to accomplish. And then some of those examples, again, of customizations that we've done, if these strike any interest, are again those new variables. We have 100-meter wind in the hourly forecasts that are available, and we are currently working on solar, being able to incorporate additional variables going forward. Really expand out the portfolio of all the offerings that we have. Those larger ensembles that I just touched on, and then being able to again incorporate this into your current systems, whether that's automated alerting when a certain temperature hits or a certain variable that you are hyper focused on goes through a certain threshold, being able to make sure that you're able to have that notification system built in. We can create weather visualizations and dashboards. We're really focused on making this as easily consumable. So when we think about democratizing access to this, it's not just through you have to be a meteorologist or have a PhD in weather, but how do we actually combine the benefit of our weather forecast with our AI and kind of our platform approach to AI of incorporating Gemini and other chatbot features that allow it to utilize that data, perhaps you have your own observational data or your own weather data, and really being able to bring those two things together in more of a natural language query experience. And so if you want to build out any of those different use cases or start to brainstorm about what that may look like, we're happy to go through that scoping process and see how we can best help. And then the last one is really around data integration and APIs. Again, being able to utilize the data that you currently have and incorporate it into the models or incorporate it into your workflows so that you can have all of these things in one centralized location and more of that single pane of glass view. A lot of customers have multiple weather providers that they're currently utilizing, but they're not centrally viewable. And so that makes it challenging when trying to evaluate what is the right forecast that I should go with during a specific event and which one is actually the most accurate. So as I touched on WeatherBench earlier, but also making sure that you're really thinking through how do I compare in real time all the different forecasts that you have and being able to do that evaluation effectively. So I will pause here and open it up for questions, comments. I know we have a lot of academics in the room, so a scathing rebuttal if anybody has one on weather and weather AI. But thank you so much for listening about our weather AI solutions and WeatherNext and everything that we're bringing forward. We're really looking to see how we can best partner.
Nellie, that was fantastic. Thank you for that presentation. And we are going to start selecting some questions from the Q&A channel. And I noticed this week some people also inserted their questions into the chat. And so we'll be clear next time that the chat is for community conversations and the Q&A button is questions for the speaker. But I'm going to go through and try to dig those out this week because there were some really good ones in there as well. And I want to make sure that we get to those. But first, let me look at the Q&A channel and see. I'll start pulling some of these out here. This is a really important question for using an AI-based method as opposed to a simulation-based method from Joseph Schoonover. He says, if you have a systematic error in a forecast, what does the triage and bug resolution look like in an AI model in comparison to a traditional NWP model? He's curious about how you delineate between a problem in the underlying training data and the AI source code or even chosen AI algorithms. So you want to speak to the difference in trying to debug the cause of a bad forecast in an AI model versus a simulation model?
Yeah, great question. And you definitely hit on one of the things that with the AI models, it's a little bit more of a black box sometimes as to how these forecasts are produced. And so we do have certain levels of visibility into how different metrics are calculated, how different forecasts come about. But one of the areas that we're really exploring is having greater levels of explainability. So being able to say, okay, this forecast said that on Tuesday, there's going to be a massive rainstorm over Oklahoma. Why is that? And being able to actually have the model be able to say, it's because of this pressure element or experience that's happening in the atmosphere that's then affecting the temperature in this location that's then creating this rainstorm in Oklahoma. Getting to that level of explainability is kind of the holy grail for AI weather models, of being able to actually track backwards so that you can check and make sure that those forecasts are accurate and that it's really thinking through all of the different steps of how this is being generated. I will say that right now, the teams have done a lot of back testing and historical evaluations on the data. And one of the things that's really important is as we've trained our models every year, we incorporate the data from the previous year. However, we go up until that year. We don't give it the year of data that we currently have. So if we're training a model for 2025 weather forecast, we will give it up till 2024 weather data so that we're not giving it the cheat sheet of what we can know. Oh, we know what happened in January through March of 2025. We're not going to give it the forecast of what it was when it's generating those forecasts. So we're really focused on making sure that we have a level of evaluation that is accurate in not giving the model kind of the cheat sheet code, but having it actually learn, and then we're able to compare what that forecast is to the actuals of what occurred.
Yeah, I mean, that same problem exists in numerical weather prediction with simulation-based codes anyway. How do you know if it was the initial data or something about the model that you're using when it's nonlinear dynamics and you're extending the forecast over an extended period of time? So in fact, in prep for your session today, I pulled out my old book, Chaos, from James Clyke. I checked today, it's 38 years old. And the first chapter is about numerical weather prediction and the challenges and how that inspired some thoughts about chaos theory. Here's another great question from Rafi Lav. What about extreme events, as we are going into more extreme unseen events more and more? So how does an AI model keep up with the fact that its training data may be over historical data that might not be as representative of the increasing frequency or new types of extreme events?
Well, there's a lot of promise in this area actually for AI models. One of the really unique things, and I showed that example of Hurricane Beryl, our models were actually not trained to predict hurricanes. They were trained to be able to predict weather forecasts. It just happens. This is kind of almost like the latent space of the model learning, things that we didn't predict that it would be able to learn. It learned how to predict a hurricane. And again, not something that it was trained on specifically to be able to know what it was, but it got really good at. And so when we specifically with WeatherNext Gen, a huge focus of creating that model was really to be able to have more of those extreme circumstances be able to be captured in the different ensemble data that we are generating. So that's an area that we are really focused on being able to say, okay, if we expand out the number of ensembles that a model can capture, can it go ahead and actually predict those events that perhaps have not occurred in the past? But again, that the model may have understood certain subtleties based off of the data that it was trained on, and then be able to predict what those new occurrences can be. It also, surprisingly enough, was able to predict Hurricane Lee went through Nova Scotia a couple years back. And it's very rare for a hurricane to go that far north into Canada. And it was GraphCast at the time, WeatherNext Graph, now it was able to predict Hurricane Lee effectively. And again, something that has never, if very rarely, occurred. So I think we're continuing to see these models evolve and get smarter over time, but very excited for what the capabilities are that we continue to discover in being able to have more of those tail end factors be captured going forward.
And Nellie, I'm going to ask a related question to that. How often are you incorporating this new data, some of which may be, influenced by climate change? It might be incorporate more extreme events, et cetera. How often are you retraining the models and incorporating new data? Is it every year, every 6 months, every 3 months? How often do you do that?
So for the public models that are currently generating the forecasts in BigQuery and Google Earth Engine, it's every year we're updating those models with new data. However, we have lots of different models in development right now internally, and those are getting updated more frequently as we continue to test and go forward. Great.
Now I have a technical question here from Bill Turner. Has your weather application taken advantage of the recent marriage of Kubernetes on the same plane as NVIDIA using the NVLink from a previous session? If so, does the new parallelization return recognizable data improvements? I'm assuming it means recognizable forecast improvements there. So I'll rephrase that question. I'm assuming he's asking more about the training of the model. Is it leveraging all of Google Cloud's best and greatest performance capabilities in the training of that model? And also, can you say anything about what technologies are being used when you actually want to infer a forecast?
Yes, so it is leveraging all of Google AI's capabilities and the latest and greatest technologies that we have. We were very, very thrilled to see at Google Cloud Next, which just happened a couple of weeks ago. During the keynote, Sundar, our CEO, actually talked about WeatherNext now living on Vertex and being able to bring these weather AI models to Vertex so that customers can access them directly on the platform and be able to have them natively in the AI environment that we've created. So yes, we are leveraging all of those tools and being able to bring the latest and greatest, and also make sure that you all are able to have access to the latest and greatest in the easiest way possible.
Great. I'm going to ask another question from Joseph Schoonover here. For longer timescales, it becomes increasingly important to incorporate ocean dynamics. Are there plans to build out similar models based in physical oceanography, general circulation models? And he gives some examples of some of the circulation models and the available data.
It's a huge area of interest for us right now. Customers obviously have expressed that very similar opinion of wanting to be able, obviously on land, also over the seas. Right now, our models do global forecasting. So they can calculate wind speeds over the oceans. They can calculate weather effects over ocean regions. However, as we know, having that actual ocean data is a really great tool in being able to have even more accurate predictions. And so much can change when we think about even kind of wave height and what that can do in again, a shipping situation, or being able to see how you should affect a route or a cruise line, and being able to make sure that you're planning accordingly for those different elements. There's a lot there that it's the ocean data. One of the challenges is that there's just not consistent ocean data for global coverage at the level of granularity that we have for weather data. I guess you could say above above sea level versus below. So it's an area that we're continuing to explore different data sets, different methods to try to do more accurate predictions, but a continuing area of research for us.
Nellie, you hit on the wave heights question, and it brings back a former life position and location. I used to live in San Diego, and I had two groups of people that were always interested in the wave heights. And one was DoD. They cared about wave heights for various potential operational missions. And the others were all the surfers that I hung out with who cared about wave heights as well. So if you can get wave heights and infer those with great accuracy, you'll please both those two groups. I saw a question in chat that was really good, asked by Katerina Tavara. And in chat, it's more of a community kind of question. And in fact, it was answered in the community by Felix, but I wanted to repeat that question here and see if you wanted to add anything to it. So Katerina asked, are there places on Earth that you are more accurate than others, or the results are equally the same everywhere? Felix responded to Katerina, yes, the 0.25 degree resolution, for example, will probably not be enough to resolve weather in densely mountainous regions like Switzerland, which is where Felix lives. Do you want to address anything about regions and topology and geography and the accuracy of our models and where they work better and where they struggle, maybe not struggle worse than numerical weather prediction models, but still have more challenges?
Yeah, Felix answered it pretty much perfectly. We, on the whole, again, on the whole, like when we look at the entire Earth, averaging, it's equal performance. So it's not like in North America we do better than in Asia. But we have global coverage around the world. However, when we do look at specifically the mountain regions, when it comes to wind prediction, that is incredibly challenging to do. At the 0.25 level resolution, we are continuing to get more granular and more accurate. But the mountain regions do pose some additional challenges as the atmosphere continues to change there in typically a more frequent state, and also with certain variables, it's just harder as you work your way up into the atmosphere at those different pressure levels. Great.
Nellie, with that, do you have any final comments that you want to share before we move into final announcements for today's session?
Yes, the final thing that I'll leave you all with is really just the excitement of what we are building with weather and how this can have a positive impact in the world. Obviously, there is an entire weather ecosystem out there right now, and we are a small piece, but we really want to start to help people reimagine what's possible when we have more accurate weather forecasts for resiliency, for efficiency, and for the accuracy of being able to predict what's coming, how we can go ahead and build our businesses, our lives, and our communities with the strength and resilience that we're going to need as we move forward into this world. Really just want to to thank you all for being here and for listening. And hopefully this gets all of your brains going with new ideas of how you can incorporate weather and how you can continue to have this work into your scientific work, your academic research, and your business organizations to be able to have an effective path going forward.
Yeah, this is super exciting work, and it was great to see it mentioned at Google Cloud Next on the keynote stage and everything. So thank you so much for being with us here today, Nellie.